So for the first speaker is going to be Ali Sheikholeslami. Let me introduce him. Ali is a professor of electrical and computer engineering at the University of Toronto, Canada. He is co-author of a graduate level textbook titled Understanding Jitter and Phase Noise, a system perspective. And he is well known as the author of regular column series in the Solid State Circuits magazine titled Circuit Intuitions. Ali is currently serving as the educational chair of A-SSCC and as the vice president education for the Solid State Circuit Society. So please welcome Ali.
Thank you, Sungtak, for your introduction, and thank you all for being here today. I understand that we have actually students from all across Japan, Korea, and China coming all the way to Hiroshima for the very first Circuit Insights of the Asian Solid State Circuits Conference. Thank you very much for being here. I also like to thank the conference committee of the Asian Solid State Circuits Conference and the Solid State Circuit Society for sponsoring this event. The title of my talk is Noise and Distortion. And as you can see here, I'm just trying to provide you an abstract in the title where noise is contaminated by noise and distortion is distorted by distortion. So the idea is that when you have noise, it's just an additive signal that you add to your original signal, and it makes it hard to see because of these noisy background. And distortion is a different beast in the sense that you have to turn your head around in order to figure out what the actual signal is. Song Tang already introduced me, but let me just tell you that really for fun, these are the final two activities that you can see on this list. I'm writing the Circuit Intuitions for Solid State Circuit magazine, and if you haven't had a chance to read any of them, please do so. They are meant for undergraduate students and maybe starting graduate students. Hopefully you will enjoy them. And the other fun activity is the event today, Circuit Insights. As Song Tang mentioned, we started this activity back in A-SSCC 2021 when it was the first year of pandemic and we couldn't get together in person. So this event was virtual in the first year. And I do remember in the first year we invited gurus in our field, including, for example, Professor Willie Sanson, who unfortunately passed away earlier this year. And as part of that, we had a panel, and we asked a panelist to tell us, or to tell the new and aspiring students, designers, what advice they have for them. And this was the advice that Willie Sanson gave, and it stuck with me. He said, there's really two that I'm highlighting here. One is that you have to understand what circuit design means at the system level, because circuit design is really sitting below the system level. And the second thing he mentioned is that you have to know something about noise and something about distortion. And just to honor his advice, I decided to write this article series on noise and distortion. In fact, two of them already been published in the magazine, and I just submitted the third one. So what this talk is about is a review of the first two and a preview of the next one that will come out maybe in a month or two. So here's the outline of the talk accordingly. I'm going to tell you what is noise, how do we characterize noise, and how we reduce noise. The second part of the talk is what is distortion, how do we characterize distortion, and how we reduce distortion. It's like any engineering work, right? First, you look at the problem, you ask yourself, what is it that you're trying to solve? And once you know what the problem is, the second part is to characterize it and to find out what that beast is exactly and how we can quantify it and then communicate it with other engineers so we can all together solve a problem. And once you understand the problem, as you know, you're already half there to the solution, and that is how to reduce it. So we're going to apply this very engineering principle to noise and distortion, and we'll go through this. So what is noise? So I asked ChatGPT to create an image of a butterfly where the left half is intact and the right half is contaminated by noise. And this was the first attempt. In fact, ChatGPT did a great job. And as you can see, the left half is exactly the picture of a butterfly as you expect. But the right half is not distorted by added noise to it. And what it means is that you randomly add colors and pixels to that original image. You can still recognize the butterfly on the right side. But the fact is that the right side has this unwanted random signal that is added to the desired signal and is degrading the quality. This is, in summary, what noise is all about, in fact, in terms of image. But now let's look at this in some other context. I think the context that we all know is noise in audio signal, right? You have all been in a party and you like to have that conversation going with your friend, but there's a lot of other crosstalks. Everybody else is talking. Or you want to talk and all of a sudden there's a big engine running beside you, or there's a fan in the room that is bothering you. It's just because it makes it so much harder to get the signal that you want. The desired signal is harder to recognize once there is noise. So here I'm showing an example where you have the desired audio signal and you like to amplify it, but beside you there's noise. And again, this could be crosstalk, it could be somebody else speaking, or it could be a fan, whatever other noise source that you have. And by the time they get to the microphone, they add up. This is the air pressure being added up by two sources. And now you're going to amplify this. Now, of course, if you look at the output of this microphone, you see there's a voltage signal that is signal plus noise. So this is S of t represents the desired signal, and N of t, the undesired or the noise, the random signal. Now, we like to amplify this because that was the purpose. We have an amplifier here in the room. In fact, I'm using the microphone, and we have an amplifier. It's interesting that, obviously, when the amplifier is going to amplify this, it's going to not distinguish between signal and noise. Both of them are going to be amplified at the same time. This should be no surprise. That's great. But it seems that in addition to having S of t plus N of t being amplified by a factor of A, there's this additional noise. That additional noise is the electronic noise. The amplifier itself creates its own electronic noise. Once you take the voice, the audio, and you move it to the electronic domain, now you're at the mercy of electrons. And the electrons have random movement because of the room temperature, because they're not at zero Kelvin, right? So once the electrons start having their own random movement, they create additional noise. And that is the subject of this talk. How do you understand, how do we characterize that noise, and how do we mitigate that noise? So here's an example of that noise that is created by electronic circuit. In fact, this is created by a resistor, as we will see soon. You just have a resistor, and because of thermal movement of electrons, they create a voltage across that resistor, even though it's not connected to anything. You can see that the noise is going up and down, obviously is random, and it goes between -5 microvolt, very small, to +5 microvolt, but it's not uniform, it's not always the same level. The noise goes up and down, and the way to characterize it is to understand the mechanism by which it is created. And interestingly, it appears like a random variable that is changing according to a Gaussian distribution that is shown on the right. So if you look at this Gaussian distribution, it says that the noise that is created, on average, the expected value of that noise is 0 volt. But it has some standard deviation, which in this example I've used 1 microvolt as the standard deviation. And as you remember from your math, if you look at the area underneath this probability density function, you can find out what is the probability of certain noise being a certain band. So in this case, to find noise to be between -1 microvolt to +1 microvolt, for example, +1 microvolt, you will get 68.3% of the probability. But if you are willing to go and look at all the noise that is created between -2 to +2, again, you look at vertical axis here, -2 to +2, then it will become 95% of the time. And if you increase it and say, what about 3 sigma, which in this case will be 3 microvolt and -3 microvolt, then the probability will go much higher. And of course, as you go beyond this, the probability will become less and less. So we're dealing with a random variable as a function of time, and it happens that in many cases, the distribution of that random signal, in fact, is Gaussian. So, and we know that we usually characterize a random signal by its expected value, in this case 0 volt, and by its variance, which is expected value of n squared of t, and that happens to be 1 microvolt squared. I guess what we can call this 1 microvolt is the RMS of noise. So this is just the same picture. I'm just trying to reiterate that really what you should do is to turn this PDF 90 degrees so you can see corresponding to every value here, you can go up and find out the area underneath and find out what is the probability of noise being in that range. Now, just to give you a feel for what it may look like when you add this noise to the signal, I start by looking at signal first without noise. So this blue sine wave, as you can see, has an amplitude of 1 volt. So it goes from -1 to +1, a 1 volt amplitude, and it's at 1 kilohertz. And we like to define what is the signal power here. So this is towards characterization of signal and noise. The first thing is, what is the power in that signal? And as you recall, the power of any signal is defined as the integral of that signal squared times dt. So that is, you integrate the signal squared over a period, and then you divide it by that period. That gives you the average power of the signal. In fact, for a sine wave, we know that power is a squared, where a is the amplitude, divided by 2. Since I'm using a sinusoid of 1 volt peak, then this integral gives me 0.5 volts squared. So remember, when we say this power, this is not the power that we consume in a resistor, but if you wish to think about it that way, it's a power that we can consume in a 1 ohm resistor. If we apply that signal, voltage signal, to a 1 ohm resistor, how much heat do you generate? And the answer is that a signal, a sinusoidal signal with 1 volt peak, is going to generate half a watt in that case. But we are not looking at this. We are just normalizing to a resistor of value of 1. And so we just say half volts squared as opposed to watts, right? So that's the first metric that I'd like to introduce. The power of a signal is the average of the square of that signal, right? And that would be half a watt. Now, I want to look at the noise alone, and just to exaggerate this a little bit so you can see the concept, I've decided to use now a noise with a sigma squared that is 0.05. So you see, while the signal had a power of 0.5 volts squared, I'm using 10% of that. So noise has now 10% of the power, and it's defined the same way. So if I just decide to square the noise and I integrate it and then divide it by that period, it gives me 50 milliwatts. So this is like 500 milliwatt. You have now 50 milliwatt of noise added to it. Once you add these signals together, this is what you get at the bottom. You can see that sinusoid is clearly degraded. Now you have all these noise on top of this. And in fact, the way to characterize noise is not to go and absolutely tell you what is the noise power. A better way to say, how much is it with respect to signal? Because if I have a very large signal, maybe I don't care as much about noise. But if I have a small signal, the noise becomes all the more important. So what's really matter here is the ratio of the signal power to noise power. And that's what we call signal to noise ratio. The higher is SNR, the better is the quality of the signal, or that means less important is noise for us. So we, instead of defining a signal to noise ratio just as S over N, we tend to take the log of this because we're going to deal with a huge dynamic range. And so when we once we take a log, we can bring it to a level that we could easily communicate. And so, for example, in this case, we said that the signal power was 10 times the noise power. So S divided by N becomes 10. Once you take the log of that and multiply by 10, you will get 10 dB. So this is an example of SNR of 10 dB. And you can already tell that SNR of 10 dB is not really good for our application. If you listen to this, you will be bothered that this is so bad quality audio. Let me now go and improve this signal to noise ratio. In the blue, I'm showing a signal to noise ratio which is 20 dB. Now it's a factor of 100. So signal power is 100 times bigger than noise. And you can already see that the signal is improved quite a bit. Now, if I go and increase it one more time, this time by a factor of 1,000. So signal is now a factor of 1,000 more power than the noise. Then you see the green curve, and it looks very good. But believe it or not, even if you listen to this, you will notice that this is not a good audio. The audio that you're using in your headphone today, they are giving an SNR better than 60 dB. So that means a factor of 1 million. So the signal power, your ear is that sensitive. Your signal power should be 1 million times more than the noise power for you to enjoy the voice qualities. Now, this is related to voice and audio, but obviously, depending on what applications, you may need SNR that are much higher than this, or maybe a lower SNR would be okay. So, so far, what we talked about here was, okay, looking at the signal power and noise power, that seemed to be just one number. And that is not enough for us. What we need to know is that how that power is distributed over frequency. In other words, we need to also know how fast is that noise moving. The signal, the noise that I showed you, on purpose I limited its activity to 10 kilohertz. That means there was a filter that didn't let the noise to be moving much faster than that 10 kilohertz. But if you do not do this, the noise may have much higher frequency content. And so this is why we would go and characterize the noise in what is called power spectral density. So to put simply, you'll have the total power, but the question is that how much of that power belongs to what frequency bin? And so I'm showing you three different type of power spectral density here, and you can notice that the unit of power spectral density is that volts squared, which was the total power that we defined, over hertz. So how much volts squared you have per hertz. And you can see, we will shortly see soon, that for the resistor, that noise power, in fact, is flat. So it has frequency content at any frequency that you have, and it has it in the same proportion. We in fact, will find out that noise, that distribution is flat, and it seems it's going to go quite high into terahertz range, and it's still flat. If you look at transistor, you will see a different behavior. Transistors have multiple sources of noise, and if you look at the power spectral density, which we don't go through this lecture, but we just tell you the concept, is that you have some noise that when you decrease the frequency, they increase. So in other words, there's more frequency content of that noise at lower frequency than at higher frequency. And as you increase the frequency, it will plateau at some form, and that will become the white noise at that point. And that will become the noise floor, as we call it. And there's a corner frequency when you switch from one noise source to the other. In other words, one is dominant at what portion, and one become dominant afterwards. And of course, when you have electronic circuit, the noise, like the signal, is going through the circuit, and therefore it's going to be affected by the transfer function of that signal or that circuit. And so that circuit eventually has a bandwidth limitation, and is going to make the noise to have some limited bandwidth, as is shown here. So this is the concept of, again, these are all noise, but in one case we're showing you a noise of a resistor on its own, and that looks flat. In the second one, we showed the noise of another device, which is a transistor, and it has this characteristic. And in the third one, we say, okay, what if I have a bunch of circuits, transistors, resistors, and now I look at the output? What would be the power spectral density of the output look like? And as you can see here, it will look like the one that's shown. So let's look at resistor a bit deeper here. So I just showing you a symbol of a 1 kilo ohm resistor here. And the idea is that, of course, we have learned from our undergrads that, you know, if you have a resistor and there's no current to it, the voltage across it should be 0. And you're wondering, why would we even have noise? And the idea is that there are these electrons inside the resistor that are moving. And whenever you have a movement of electron, you have a current, right? And so there's lots of electrons, and there are lots of movements, and the overall impact of that current that is going up and down is that you will observe a voltage across this resistor. And that voltage, for a 1 kilo ohm resistor, we've measured it with an oscilloscope that has a limited 10 kilohertz bandwidth, you will see a shape like this. So this is going between -1 volt to +1 volt. And so this was the subject of many studies. In fact, back in 1928, Johnson and Nyquist were the two who actually went ahead and characterized this. And it was almost 100 years ago, as you can see. And this is what they discovered. And the key observation that was summarized in 2 papers, that were published simultaneously in the same months of the year. And these are the two. One is that if you look at the noise power spectral density of resistor, it's going to be flat, meaning that it has frequency content in all frequencies, and it goes to at least beyond the circuit's bandwidth that we're dealing with. It goes beyond in the terahertz region. We usually don't use our circuit these days. Maybe we could go to a few hundred gigahertz, but when you go to terahertz, we're dealing with different phenomena. So as far as the circuits are concerned, we would say that this is flat across the frequency. The second very important observation was that the noise power spectral density is proportional to the value of R. If you double the R, you double that voltage that you observe, right? And the other one is that absolute temperature. So if you increase the temperature, the power spectral density moves up proportionally with that temperature. Now, if you put it together, this is what we'll get, and I've shown it here on the top right. So the power spectral density of noise is equal to 4 kTr. That factor of proportionality is 4k, where k is the Boltzmann constant, and then you multiply that by T and R because we said they're proportional. In fact, if you look at this, this is again power spectral density. So power spectral density, to turn into power, you need to integrate it over frequency. So depending on the frequency of interest, if you have delta F, you need to multiply that by delta F, and this becomes the equation. That is the total power of the signal that you observe if you limit the frequency to delta F. 4 kTr delta F. That's the formula that you should probably memorize if you're going to work on circuits. Now, you may wonder what happens if I use a different resistor, but also same value. So same 1 kilo ohm, you have two options. Either you just buy 10 or 100 resistors all at 1 kilo ohm, and you measure the noise across all of them, or you take the same resistor and measure it 10 times. You measure some now, some an hour from now, and then you look at the waveform. And it's interesting because the waveform obviously look random. They're not identical, but they're random and they have the same properties. What are those properties? One is that the expected value of noise is always 0. So if you average any of these, for example, you will end up with 0 volt. It just goes up and down around 0 with total symmetry. So you get 0. But the expected value of noise is squared, which corresponds to the power of that noise. That is proportional to absolute temperature, resistor, and delta F, as we said, depending on the frequency bandwidth that you have. And in this case, for the resistor of 1 kilo ohm, if you measure it at a temperature of 290 Kelvin, which is 17 degrees Celsius, you will get approximately 0.4 microvolt squared. That means really the RMS of noise that you measure, it's also called RMS of noise, it's 0.4 microvolt. So you may say 0.4 microvolts is such a small number. Why do we bother with it? The idea is that this noise can be amplified. You like your signal, and then you can increase the amount, and it could become comparable to the signal level that you're dealing with. In fact, if you express it in terms of dB, it will become minus 168 dB per hertz. So now that we know that, okay, the noise power spectral density for a resistor is 4 kTr, how do we go ahead and model our resistor? If you have a noisy resistor, you could always take this power source and you put that in series with your resistor. So in other words, you have now a noiseless resistor here, and you have a power spectral density of a voltage source, which is 4 kTr. Now, instead of using plus and minus, I'm using a star here. The star tells you that there's no polarity here associated with noise, because we're looking at the power, and power is always positive number in this case. So we are just writing it like a star. Equivalently, like Norton and Thevenin equivalent circuit, you could try to model this as a current source. But in that case, the current source will have a power spectral density, which is 4 kT divided by R. These two circuits are equivalent. Now that you have the noise, and now I have a noiseless circuit, you can now apply this to any circuit that you're dealing with. Now, imagine that that circuit that is seeing this is noiseless, okay? Because that circuit itself creates noise. But for a moment, imagine that we assume that we have a circuit that doesn't produce any noise, but it just takes the noise from a resistor. How much that noise is going to be amplified and represented at the output of that circuit? If you imagine that circuit has a transfer function, which is shown as h of f, This is the transfer function. H of f is squared. A magnitude of h of f squared needs to be multiplied by the power spectral density at the input to give you the power spectral density at the output. Remember, in a typical circuit, when we're dealing with deterministic signal, you take the Fourier transform of the input, you multiply by the Fourier transform of the impulse response, which is called transfer function, and you get the output. But when it comes to noise, we are dealing with a random signal. So instead of dealing with the actual Fourier transform of the signal, we're looking at the power spectral density of that signal. And we multiply, therefore, by the magnitude squared of the transfer function to get the power spectral density at the output. And that is shown on this slide. Now let's see what happens, for example, if you put this resistor in parallel with a capacitor. Capacitor turned out not to have any noise of its own, but it always integrates the noise of the wire that is connected to it or any resistor that is connected to it. And so as a simple example, you see here the transfer function from here to the output of this capacitor is going to be 1 divided by 1 plus j omega RC. And if you take the magnitude and square it, and you multiply it by the power spectral density of the noise of the resistor, you need to integrate this quantity in order to get the total noise that is integrated across that capacitor. I'm showing that symbolically here on this graph. You can see I'm using two different resistors, R1 and R2, where R1 is larger than R2. So therefore, the power spectral density of R1 is larger initially. But as you know, there's an RC time constant associated with this RC circuit. So if I use a larger resistor that is going to give me a larger power spectral density, I will end up having a lower bandwidth because bandwidth is proportional to 1 over RC. And therefore, these two seemingly different R1 and R2 are going to produce two different noise profiles. But interestingly, the area underneath both curves are the same. And that means that they produce the same noise power across the capacitor. And you can see this easily through math, then that will be KT over C. To give you a feel for this, I decided to give you the values for one capacitor is 1 picofarad. What is the noise across a 1 picofarad capacitor? And if you just go and measure this, that noise will give you an RMS value of 64 microvolt. If you go to lower capacitor, you're increasing the noise, right? So this is not about resistor changing, we are changing the capacitor itself, right? Because it's 4 KT over C is inversely proportional to value of C. If I use C of 1 femtofarad, then the noise becomes 2 millivolt. All of a sudden you go from microvolt regime to millivolt regime. So you need to be very careful with small capacitances. What about the noise of transistors? Now this is where we're going beyond the scope of what I could cover potentially in this lecture, but I know that you're curious, so I want to tell you that if you use a transistor, turns out that there are two sources of noise inside a transistor. One is related to the thermal movement of electrons in the channel, and that in fact gives rise to this portion, which is called the drain current, ID F of squared, and that is the power spectral density of the current. But there's another phenomena that is related to the gate of the transistor and the fact that there's impurity inside the silicon underneath the gate that caused some trapping of electrons. And it turned out that that is creating its own noise because it's a random capture and release of electrons. And that is having a PSD that is inversely proportional to F. Now, when you try to look at this, you can actually model it as a current source at the output and a voltage source at the input. But alternatively, you can decide to merge them together and look at what we call it input-referred noise. And that is equivalently, you take all the noise and you put it at the input, then you imagine your transistor is noiseless. And that is the ideal case that we like to do for analysis purposes at least. We'd like to know if the transistor is noiseless, what is the equivalent noise at the input, and then we can go through the transformation. And in fact, this is what you'll get in that case. The input-referred noise will have a 1 over F profile until it reaches some corner frequency, and then will be flat. Okay, so with that, now we're going to go and see how can we now reduce noise, given that we have noise coming from transistors and resistors. And the idea is very simple. We said that noise has a power spectral density. So if you just decide to filter it, put a filter in front of it, you're going to have less noise going through the system. So this is in fact very easy, and I'm showing you one example here. When the input noise is flat, as you can see here, is about minus 168 dB per hertz. And then I apply a filter. This is a filter gain in blue. And once I multiply the two, I will get the red. So now the input noise is flat, and you have to take the area underneath this to find out what the total power of noise. And once I go through the filter, it reduces the amount of noise. So the noise power, which is the area under its PSC, is now reduced by filtering. You may wonder what happens in time domain with noise. And that is quite interesting because, you know, filtering noise in frequency domain, in fact, translates to limiting the rate of change of noise in the time domain. These two are related, whether it's signal or noise. So when we have noise that is moving so fast, let's say, it moves within 1 microsecond, it moves so much, right? But you know, your signal doesn't move that fast. If you have that knowledge that your signal has a limited rate of change, because you have a bandwidth, let's say, of 10 kilohertz, 10 kilohertz will give you the rate of change that is limited by that 10 kilohertz content. If your noise has a lot more content, that means noise is changing very fast. So if you look at the time domain, you tell yourself, well, my signal wasn't changing that fast, this must be noise, so let me suppress it. So that's the concept, that you can apply this in frequency domain, just apply a filter, or think about it a bit harder in the time domain and say, by limiting the rate of change, I'm now reducing my noise because I know that my signal is already limited to this value. So by me limiting the sum to that derivative, I'm not going to change my signal at all, but I'm going to reduce noise. To just show you one picture when we apply this concept, so you have signal plus noise, as you can see on the top, and now you apply a filter, and you can see the recovered signal, and you can see how close it is to the original signal simply by filtering it. Okay, let me do a quick recap, and then we go to part 2. We said that resistors and transistors generate noise in the circuit. This is different than the noise that you have at the source level. This is generated by the electronic circuit, right? And we said the power spectral density for resistor noise is flat, but for transistor is more complicated. It starts with 1 over F, and then it becomes flat. And then we said to reduce noise, simply filter it, especially in frequencies with no signal. Okay, so now let's go to the second part, which is distortion. It's another picture by ChatGPT. I asked ChatGPT to create an image with a magnifying glass, and you can see this picture is clearly distorted. If you just don't pay attention to the actual magnifying glass, you see that one eye is amplified, but the other eye is not amplified, and so that creates distortion. And I decided to apply distortion to my own text, as you can see on the right. You look at that text, this wasn't a mistake. I did it on purpose. I just changed all those fonts to different sizes, so you can see this is the concept. What if you have a signal, and you decide to amplify different portions of the signal with different gain? That is distortion, right? In one word. Let's see how it's getting this, how it's starting. So if I look at electronic circuits, I will use a very simple circuit. This is common source amplifier, single-ended common source amplifier, and it's biased at VGS, and you have an input signal, and you look at the output signal, and then you are going to draw the both. So we look at VN. VN is a signal, a sinusoidal signal with 100 millivolt amplitude, right? 200 millivolt peak to peak. And then I look at the output and I realize that, wow, this is not symmetric anymore. In fact, the negative excursion goes all the way to minus 0.6, but the positive excursion is limited to about 0.4. You can see that the top part is being compressed, where the bottom part is having room to amplify. So this is the concept that we just talked about. If you try to characterize this, we typically just go and draw V out versus Vn while we sweep Vn, and you can see the transfer curve looks like this. This is clearly a nonlinear function. It's not a linear. So the portion that is linear, of course, will amplify the signal. But as soon as it plateaus and saturates at the top and bottom, you're dealing with a nonlinear behavior. Now, this nonlinearity has two interesting properties. One is that you can clearly see that at the top, when you apply a negative input, the maximum output is limited to 0.5. But when you apply a positive input, the negative output is going to go to minus 0.6 or so. So that was exactly what we observed in the previous case. The other portion, which is more important, is that you take the derivative of this transfer curve, and that is giving you this small signal gain at every voltage level. And that small signal gain is shown here at the bottom. You can see this is totally non-constant gain across the input signal. So for the input signal at a lower level, you see almost zero gain. Here the derivative is 0. If you go to very high value, you also get 0. But the gain, even for the region when we consider the small signal, is going to change quite a bit from minus 8 volt per volt here to minus 2. So there's a gain difference. And that was exactly the picture that I showed you earlier. You take an image, you magnify some portion of it with one value, you magnify the other portion with other value. That is exactly the same concept. So this is both result in what we call signal distortion. So the question is that, okay, now we understand it, but how do you characterize this? And the idea is that we use Taylor series. So we know that if you have a function that is nonlinear, there's always a Taylor expansion for it. So I've just moved from V in to X because it's just easier notation. Imagine X is the input to that single-ended amplifier that I showed you, and the output is Y. So I can look at that function, and I write it as this form, Y equal f of x, and I can use a Taylor expansion to write it in this form. I've not used DC in this case because we could easily eliminate the DC at the end. And imagine that input is a sinusoid, so A sine of omega t. Once you apply this sinusoid to this function, which is nonlinear, you end up with squaring these and making it to the power of a third and so on, and you end up with all these different terms. And when you add them up, this is what you get at the output. So remember, the input is a single sinusoid. When I mean single sinusoid, I mean a sinusoid at a fixed frequency, omega. You look at the output, all of a sudden you have sine of omega t, of course, but then you have sine of 2 omega t, you have sine of 3 omega t, you have sine of 4 omega t, and you have all sorts of frequencies that show up, all multiple integers of the initial or input tone, as we call it. So how do we measure now the nonlinearity here? It's very easy with this, because what you can say is that, okay, out of all these signals that I see at the output, my desired signal is this, right? You agree? Your desired signal has a frequency of omega, so you're only interested in sine of omega being amplified, but not seeing 2 omega or 3 omega. So what do? We just, again, do the same concept. We measure the power of the desired signal, and we measure the power of distortions. The rest of those are called distortion terms, right? Second order distortion, third order distortion. We add up all their powers, and we have the power of the signal, and then we define the total harmonic distortion, in this case, as the power of distortion divided by the power of the desired signal. You notice that this is like inverse of what we decide for SNR. In SNR, we defined signal divided by noise. For I don't know what reason, we decided to use the opposite polarity. So in this case, the total harmonic distortion is the power of harmonics. This is unwanted, divided by the wanted signal, right? Which portion of your signal is bad? Maybe this is a better characterization of actual distortion, because your signal is what you have. You want to compare it against your signal. So in other words, in this case, when you have a total harmonic distortion that is larger, that means it's worse. You have more distortion. But it's very clear, because the good news is this. When you have a signal that has multiple frequencies, it turns out their power add up linearly, right? So in other words, they're orthogonal to each other in the frequency domain. So all you need to do is just take this h1 squared, h2 squared, h3 squared, and then you have all the terms that you need. And then you can either divide it, and that will give you total harmonic distortion in terms of percentage, or define 10 log of this and then express it in terms of dB. So again, important concept is to define the total harmonic distortion. And we define the total harmonic distortion, in this case, as 10 log of power of the harmonics, total power of all the harmonics, divided by the total power of the desired signal. The ratio of the two, log times 10, gives you the total harmonic distortion. Now, let's get that output signal that I mentioned on the previous slide, this y of t, and feed it to a spectrum analyzer. Or simply go ahead and find the FFT and see how that will look like. And this is the power spectral density of that signal that we see. So interestingly, actually there's some DC value that shows up. We said we can eliminate it, but it does appear in our circuit. And then you see in this case, I'm applying a 100 megahertz sinusoid with 200 millivolt peak-to-peak amplitude to the input signal. So the output seems to be having that, but it's got minus 8.6 dB of power, minus 8.6 dB. And then there is a second harmonic, third harmonic, fourth harmonic. As you increase, if you look at the higher order, the power of those harmonics become less and less. But what is really important is the second harmonic and third harmonic. They usually dominate the harmonic power that we're dealing with. If you just use the equation I gave you on the previous slide and find out what is the total harmonic distortion, you find out for the signal that I gave you, that is 13.2%. So that means the noise power is approximately, not the noise power, in fact, the noise RMS. The noise RMS is 13% of the RMS of your signal. And that is considered a large distortion for us, okay? Now, you also see that at the bottom, it has the thermal noise. So that was the thermal noise that we discussed before. There's a level, but that thermal noise is usually far below what you can see in terms of the harmonics. These are also called the spurs. And I want you to recognize a major distinction between noise and distortion. Noise is usually a continuous flat at the bottom of these figures. And these spurs or harmonics are showing at spikes in this figure. So these are the result of nonlinearity of the circuit, whereas noise shows up at flat at the bottom. If I increase the input signal to 400 millivolt peak to peak, obviously I'm now going into the more nonlinear territory of this amplifier, and that is going to make this even worse. In fact, if I look at this, the total harmonic distortion is now 22%. No, I didn't change anything. I just changed the input signal amplitude. So that tells you that the total harmonic distortion is a function of input signal. The larger the signal, the more chances are that you will get distorted. And that is, in fact, in line with this. So the question now is, how do we reduce this distortion? Now we know how to characterize it, how we reduce this. And there's two techniques that I'd like to introduce to you. One is use differential circuits. If you use differential circuit, so imagine that f of dot here, that function is a nonlinear function we talked about, and then you apply a v in, you divide your input to half. You give half of it to this, and then you provide minus v in over 2 to the other half, and they go through both the same nonlinear function, and then you find the output differentially. As soon as you find the output differentially, look what happened to this Taylor series. You have y1 equal to this, y2, which is the output of this, like this, and now you subtract the output of these two to make a differential output. And all of a sudden, x squared, x to the 4, all the even order x are gone. So by finding the difference between the two, you can get rid of all the even harmonics in your signal. And that is going to really improve your total harmonic distortion. Let's look at this in an action. So I've used now a differential amplifier. And if you can think about it, approximately you can say that, well, this looked like especially if you imagine that this node in the middle could be virtual ground. You have a common source amplifier on the left, which you feed it Vn over 2, and you have one on the right when you feed it minus Vn over 2, and then you take the output and you subtract it, essentially implementing this function. But look at the outcome. The output versus input at least is symmetric, still nonlinear, but it's symmetric, right? It has odd symmetry. In fact, you can easily prove it in math that this is odd symmetry. And when you take a derivative of a signal or a function that has odd symmetry, you get even symmetry. Look at the gain. The gain variation still exists, but at least is symmetric. And that means you're now getting rid of all the even order harmonics. And to see this, look at this. The black shows the previous figure I showed you for the single-ended amplifier. The red shows the one for the differential pair. Now look at the difference. All the even harmonics are gone. DC is certainly gone. There's no DC tone and there's no DC power anymore. And the second, fourth, and so on, all the even ones are gone. And so you can now go and recalculate your total harmonic distortion, and it turns out that the total harmonic distortion is now 5.3% as opposed to 13%. So from 13% distortion in a signal, you went to 5% distortion simply by taking the signal differentially. So what else can we do? This is step one. Use feedback. Feedback can really reduce distortion, and that is very interesting. So look at this block diagram that I'm showing here. You have input, output, and the relationship between two is shown in red. This was the differential pair that we just looked at, okay? So we already got rid of the second harmonic distortion, and now we're applying it in a feedback. In a feedback, you take the output, you multiply by a factor of beta, a feedback factor, and you subtract it from input before you feed it into your nonlinear amplifier. Now, once you do this, this is what's going to happen. This red curve, which is showing the input-output relationship of the circuit without feedback, that means open loop, is going to turn into green, which is input-output relationship with feedback. You already can see that the nonlinearity is reduced. You see less nonlinearity. And if you take a derivative of these two to find out what is the small signal gain, you see that the variation in gain in red is quite a bit, but the variation in gain in green is very small. And in fact, these two are going to contribute to reduction of odd order harmonics for us. I want to emphasize one thing here is that how is that working? Looks like magic. If you look at the signal and imagine that the input signal that you're applying to the feedback Vn has a level which is here, okay? So that corresponds to 40 millivolt on this graph. I apply a 40 millivolt input, okay? If I apply this 40 millivolt input directly to my original function, it would create a bunch of nonlinearity. But instead I'm applying it to this, and to this it will give me an output which is here, and if you trace it back, and you want to find out how much voltage you're actually applying to your nonlinear circuit, it turns out to be 10 millivolt. So this output voltage that you can see here corresponds to an input which is 10 millivolt. What does that mean? It means that you're really not applying a large input signal to your nonlinear circuit anymore. By putting feedback around the circuit, you limit the range of input that is going to your nonlinear circuit. In a sense, it's not really magic. It's the fact that you decided not to use the nonlinear circuit when it's so bad. You just put a feedback around it, wrap it up, and now you're reducing the input that you're providing to your nonlinear amplifier. And that is the beauty of feedback and how it's applied. Now, just to implement this, and again, I show you, again, I'm not going to go through the details of how this transistor level circuit, in fact, does the exact feedback that I explained before, but the concept is that this RS, which is called source degeneration, is providing that feedback for us. And the larger RS, the larger amount of feedback, beta is increased. So you can see the transfer curve here from red when you had no feedback, that means RS equal to 0, all the way to a very large RS, which is 1.5 kilo ohm. And you can see that automatically, as I increase RS, I'm reducing the nonlinearity. In terms of input-output waveform, input is 100 millivolt signal, and the output, again, is going to reduce in amplitude as you increase feedback. In terms of the small signal gain, you can see the variation goes lower as I increase feedback. So now let's put this into the spectrum analyzer and see what happens to the power spectral density. You can see this red is the one without feedback. So without feedback, we had the total harmonic distortion, which was 5.3%. With feedback now is 0.2%. What a major reduction in total harmonic distortion. Now, if you look at the curve, do you actually see any of the spurs? You almost don't see them. They are probably at the thermal noise level or even lower, so that's why we cannot see them. You only see the actual harmonic. But in this process, something happened. The actual tone was minus 8.9 dB when you didn't have feedback. Once you went there, it's minus 19.4. So the gain reduced. This is the price you pay. You reduce gain, but then you can improve distortion significantly. Now, this is not the end of story. In fact, we can go on and say what happens when we have noise and distortion and then define signal to noise and distortion ratio. But I figured that may go beyond the scope of this lecture. But I thought that I started with Willie Sanson, who was my mentor and talked about importance of noise and distortion. And I'd like to end it with something from his book, that Analog Design Essentials, which was published in 2006, served many of people in my generation, and I believe is still useful for your generation. And in that, I borrowed this figure from it, when it shows that you have input signal on the horizontal axis and output signal on the vertical axis. What happens when input signal becomes very small? When input signal becomes very small, it compared to noise, and essentially what you see out the output, you see noise, right? That is initially, and that is the concept of SNR in that case. But then when you go ahead and increase the input, you started to introduce distortion. I can see this nonlinear dysfunction that we had, which is supposed to be aligned ideally. It doesn't go below this because now essentially you're limited by noise in the output, right? But when you increase the input signal, your output signal goes up linearly. But if the input goes beyond that, you get to the nonlinear region and you start to see distortion. So this concept of signal-to-noise ratio, total harmonic distortion could now be expanded into signal-to-noise and distortion ratio. And if you find it interesting and exciting, I really invite you to go to graduate school. This is the topics that goes beyond the scope of these circuit insights. So this brings me to the summary. This is what I talked about. I said noise and distortion are really two mechanisms by which the desired signal is being degraded, right? But they're two different beasts. So noise is characterized by its random distribution and its power spectral density. That's what we said. And we said noise power spectral density is a powerful tool to understand noise when it navigates through the circuit, because you can multiply it by the magnitude of transfer function squared, find its power, find its shape, and then essentially manipulate from the beginning of the circuit to the end to see how noise affects different signals in your circuit. Distortion, on the other hand, is a result of circuit nonlinearity, right? This was because of nonlinearity. And it gets worse, of course, with larger input, because that nonlinear behavior gets worse with larger input. Distortion is, we characterize it by total harmonic distortion, but if you want to be more accurate, you can just say we can characterize distortion by looking at every spare, by every new harmonics that is generated. What is the power of every harmonic that is generated by the circuit but did not exist at the input? That is how we characterize distortion. We said that differential circuits effectively eliminate the even harmonics. That's great, but remember that's there's other nonlinear or non-ideal effects that we have to be careful, but that goes to graduate school. And then finally, I said feedback can be used to equalize gain. We saw that the variation of gain as a function of amplitude goes much lower when you use feedback, and that is helping reducing the remaining harmonics. Before I end this lecture, I want to say that there are many SSCS resources that is available to you. I already mentioned that you can look at Circuit Intuition's article. In fact, part 1 to 3 is all about what we discussed today. Maybe because this is written, there's a bit more context. You can look at those. There is an article in every issue of the magazine that is called A Circuit for All Seasons. I believe now it's called The Analog Mind. That's written by Behzad Razavi. And Chris Mangelsdorf, who used to work at ADI, he writes great articles on shop talk, what you didn't learn in school. So I think that will be a very nice resource for you to look at. There is a YouTube channel of Solid State Circuit Society, and that YouTube channel, if you go there, you just click on playlist and look at all the circuit insights in the past. In fact, including the panel discussion that we had with Professor Willie Sanson. So please take a look at those. Those are all available to you. And in fact, this Circuit Insights today is being recorded, and we will post it on the same YouTube channel. So once it arrives, please go ahead, let your friends know, and look at them. So I've included the past Circuit Insight on SSC's YouTube channel. It seems like I forgot to put SCirc 2024, but if you look at the, you go look at the playlist video, you will be able to see SCirc as well. Again, I also want to include that seminal book by Willie Sanson that talks about analog design essentials. That is the end of my presentation. Thank you very much for your attention.